For decades, our model of a black hole has been the ultimate dead end, a cosmic trash can with infinite gravity, where stars, planets, and light itself are swallowed by a dark funnel and destroyed. But there is a requirement at the bedrock of quantum mechanics. Information is permanent. It can be scrambled or hidden, but the universe keeps a perfect ledger of every particle's unique quantum signature. This creates the black hole information paradox. If quantum mechanics says data lives forever, but black holes appear to erase everything they consume, our understanding of physics is broken. This crisis began with Stephen Hawking's discovery that black holes eventually evaporate, potentially taking the information they hold with them. To resolve this, the Kosmos Institute of Systems Theory uses the 7ES framework to analyze a black hole like a piece of computer hardware. We look past the gravitational shadow to identify the specific subsystems for input, processing, and output. When analyzed as a system, the dead end disappears. We find a maximally efficient quantum computer, operating at the absolute limits of physical law. The teardown begins here. This photograph of a black hole shadow captures the event horizon, the physical interface where the system meets the universe. Instead of merely swallowing matter, this boundary acts as a translator. As a three-dimensional object falls inward, the interface flattens its physical properties, encoding them as two-dimensional data onto the surface. Information here is tightly packed, saturating the Bekenstein bound, the absolute physical limit on data storage. The event horizon is the universe's ultimate data storage membrane, preserving the quantum blueprint of everything that crosses it. Once that data is encoded on the surface, the black hole begins its primary operation. It functions as a processor. Through fast scrambling, the system redistributes quantum data across its entire surface area, mixing the information so thoroughly that the original state becomes unrecognizable. This mixing occurs at the universal speed limit for quantum computation, the Margolis-Levitin bound. It is the fastest possible rate at which any physical system can transform information. By operating at this threshold, a black hole scrambles information faster than anything in the known universe. It is the gold standard for processing efficiency. A complete system requires an output. For a black hole, this is Hawking radiation, the steady leak of particles back into space as the system slowly evaporates. Over trillions of years, this radiation was assumed to be random thermal noise, a byproduct of evaporation that contained none of the data. This chart shows the page curve, which tracks the entropy, or the randomness, of the radiation over the black hole's life. Initially, the entropy rises as the radiation appears random, but halfway through the system's life, the curve begins a symmetrical descent back to zero. In a closed system, dropping entropy indicates that the radiation is becoming ordered. This descent means the outgoing particles are carrying specific quantum correlations. The radiation is no longer noise. It is the scrambled data being returned to the universe in a recoverable form. The information paradox is resolved through the system's architecture. The black hole perfectly preserves, processes, and eventually outputs every bit of data it ever consumed. Applying the Kosmos Institute's 7ES framework shows us a fully balanced machine. We see a system that manages inputs, performs high-speed processing, and provides a clear output. This machine maintains stability through active and passive feedback loops, some acting in milliseconds, others spanning trillions of years. This analysis suggests that, at its foundational level, the universe is constructed entirely of information. Material objects, like stars and planets, are simply the medium the information uses to travel. Black holes are not errors in the fabric of space. They are reality itself, operating at absolute peak performance.